Howdy, everybody. I'm here for day 12 of Advent to Code. This one was a very interesting one for me. Um, the part two was particularly hard, but let's just get into it and we'll talk about it. Anyway, I've really enjoyed. Before we start, I should say I've really enjoyed seeing some of your solutions and stuff like that, and going through them and doing the reviews and stuff. So keep sending those. It's always fun to see what's going on. Okay, so this was called Garden Groups. And the gist of it is you're given a garden plot like this, and you're supposed to kind of find regions of plots. So all of these A's are in a region, all these C's, these E's, these B's, and D's, they're all in their own regions, right? And then you're supposed to figure out like the area and perimeter of that region, right? So, and you can use that area and perimeter to then calculate like the total cost of building a fence around each of the regions is what you're doing. So that's what this is here is like we can talk about that more later. But the idea is then so like the question you have to ask yourself when you're solving this problem for part one at least is okay, well how do I find these regions in the graph? And then once I do that, once I have like this region, how do I figure out its area and its perimeter? I mean, it turns out you don't have to think about it too much. The area is pretty easy, right? It's just the number of plots within the region. So for that case, the hardest part is just like, how do I find the region? And then the second part maybe takes a little bit more thought is like, how do I find the perimeter of a region? Right? This one's really you can think about like if you're looking at this, I think it actually shows you. Yeah, if you're looking at it right here, the perimeter has like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this A's perimeter is 10, meaning, and the way that you can kind of think about it is like any A within this region starts out with like a perimeter of 4, and then any A adjacent to it subtracts from that, right? So the idea is like this A, for example, has this A adjacent to it. So this is not part of the perimeter, right? But this one is empty, this one is empty, and this one is empty. And so these three are part of the perimeter. Like this is on the edge is the way to think about it. And so that's how you go out solve. That's what it wants you to figure out is what is the area and the perimeter. And then when you figure that out, you can then just you multiply those two values together to get the price of the fencing. And then you add all those values up to get the total price, right? So they give you a slightly more complex example. And the reason they do that is you can see in places like you can get weird things like all of these O's are technically one region, and these X's are each their own region. So even though these all have the same X, they are actually 4 different regions that are the same plant, but in 4 unique regions. So, this has an area of 1 and a perimeter of 4. And this has an area of 1 and a perimeter of 4. Right? So when I went to solve it, like the first thing that was going through my mind was like, okay, well, how do I figure out what the regions are? And this actually takes me back to like one of my very first programming interviews. I was asked to implement a flood fill algorithm. The idea being like, let me go to my. If you have like some contiguous area like this, and you're in Microsoft Paint or whatever, and you click like the fill button right here, how does Microsoft Paint know to like fill in this entire area, right? And I happen to have, been taking computer science classes and stuff like that, and so I had never done the flood fill before, but working with the interviewer, I was actually able to like come up with the recursive solution, right? And today is now knowing this, I'm basically doing like a breadth first search, going through all the things and just tracking all the ones that I hit, right? And so like, what does that look like? Like if you imagine there's like these blocks like this, or these plots, I guess, and this is where I'm at, and I'm in A, and let's say these are A's, these are A's, these are A's, these are A's, but this is like an O. Like, how do you solve a flood fill? You obviously want to track where you've been, so you have like a visited list, and you say like, okay, I'm here, so I'm going to mark this on my visited list and add this to my thing, right? And then I'm going to look at all the neighbors, right? So I'm going to look at this neighbor, and this neighbor, and say, are they ones? And I'm going to just do it recursively, right? So I go down here, I check this one off, and then I go over here, I check this one off, I go over here, I check this one off, and then for each of these, I'm just going to ask the same question, right? This is a little weird. I don't know why I'm doing it this way, but so then when I'm here, I'll say, okay, how about here? Oh, I've already done that one. How about here? Oh, that one's new, so I'll add that to my list. And then when you get here, you maybe say, oh, how about here? I've already done that one. When you get here, I've already done that one. And then when you get down here, you say, oh, that one's not in the list, so I'm not going to count it. And you just go through all of them and you do that eventually, right? That's the way a flood fill works. And I mean, that's essentially what this is asking you to do, is like a BFS, DFS, or flood fill just for each of these values. And so that's what I actually do in my code. Let's go look at it right now. I have a couple helper things. So again, I have a point. I call it a plot because it's like a plot on the garden. And you can see I have these neighbor values, which are like the neighbors in each of the directions, north, south, east, and west. And here's my plot, and then I implement add a couple ways for it, like I've done before in previous videos. And then I create my garden. And then within my garden, I can say, hey, give me all the neighbors of this given plot. And all this does is it goes through that neighbors array up above, and it says, are they in my garden, right? And so that finds all the neighbors. And then when I'm trying to set up the regions, I can look at that and say, I think I actually do it down here. I can say, hey, give me all the valid neighbors, right? So how do I go about finding all the regions? Well, I've tracked it here. I have a vector of all my regions, and then I have a visited list, right? I don't need to go visit some value that I've already visited in a region, or as I'm looping through it. But then I just basically I loop through all of the plots, right? So the idea is you're going to start here and then try and do the flood fill, and then you'll go here and here and here, and you'll just keep doing that until you've like done the flood fill on all of them. With the notion that, if I do a flood fill and that captures all of these, as I'm looping through all these values, I know I can skip these ones because I've already seen them, right? And so that's what the code does. I go through all of the plots and I say, hey, if I've seen it before, I can give up. Otherwise, I create a new region and I call that flood fill program on the new for the new region at the current plot that I'm at, and that has the effect of going through and doing all the stuff, right? Then, so once I found the region, I add that to my visited list, and then I push my new region to my regions list. So that's what I do here. So how does the find region work? It's actually deceptively simple, and that's the crazy thing about like BFS, DFS. These things can be very deceptively simple, right? Is I basically just go in and I say, I haven't added my visited list here, so I could actually tighten this up a little bit. It doesn't take any time to run, but I could definitely tighten it. In fact, we can do that right after this, okay? So what I do is I say, obviously my current position is going to be inside the region, right? So when I'm doing my flood fill for like this, this one's obviously going to be a part of it, right? So now I just find all the neighbors of that one, which is right here, right? So for each of my neighbors, if it's the same value and I don't already have it in the region, this is what it does. This is where I do the visited. So we won't have to, this is the equivalent of tracking the visited, right? So if they're the same value and I haven't seen it before, I just call find region recursively, right? So the idea being is like in this dot, I'm going to check this one and this one and this one and this one. and add those to my region list, and then say, hey, now I'm going to recursively call that for each of these right here. So this one will then do this one and this one and this one, but it won't do this one because it's already seen that one. And it basically just keeps doing that all over until it like fills up the region, is the way to think about it, right? So recursive can be very confusing if you've never done it before, but it's a really powerful tool. And the reason why I think it's so powerful is you can say it's a part of dynamic programming. And the cool part of dynamic programming is you can break down a problem, a large problem, into a small problem. And the small problem here is just, can I just find all of my adjacent values that are within a region, the same region? And then you take those values and just do the same thing. And if you just keep doing that, eventually you fill up and you find the whole region, right? So that's all I'm doing for my region part, right? Is I just say, go through all the plots. If I haven't seen it before, then I call the BFS or the flood fill on it. And then I just update some variables, update my regions, and update my visited node. And I just do that for all the plots, and eventually you've gone through them all. Okay. So now I have all my regions. The question is, how do I calculate the area and the perimeter? Well, the area is fairly easy. It's just the length of the region, right? So if there's 1, 2, 3, 4, 5 A's in this area, then the area is 5, right? So that part is really easy. So we just have that area, and we want to multiply that by the perimeter, right? So how do we calculate the perimeter? Well, that's what I was talking about before, is like, is this like, what is the perimeter of this area right here? Assuming there's nothing else around here, it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that, right? That's the perimeter of this A region. So like, how do I find that? Like I mentioned, by default, each of them are 4, right? If it was a sole one on its own, so these are all like filled in like this, the default here would be 4, right? So it would be these 4, right? Just to clarify. And the perimeter only changes if another one of these values are the same, right? So if this is no longer a 0 but an A, now this part is not part of the perimeter, right? So this part is not part of it, and so now it has a value of 3. And the same goes for all of these, right? If this one, then this is not. If this one, then this is not. And then if this one, this is not either. So there's potential for it to be 0. So all you really, if you think about what you're doing here, is you're just asking, hey, for A, how many neighbors do I have? So for A, I say, get the number of neighbors equal to A as well, and subtract that number from 4. Right? Like, this is the way to think about it, right? You start out with 4, find all the neighbors of A, and subtract that from 4, and that should get you how many perimeters this one contributes to the whole of the thing. And so that's all that happens right here, right? So I iterate over a region, and for each plot in the region, I do 4 minus the number of neighbors that have the same value, and count those up. And then I just sum all those, and that gives me my perimeter, right? So that's the perimeter of each region. And so I take that and multiply it by the area to get the answer for that specific region, and then I just do that over all the regions and sum that up, and that gets my answer to part 1. And you can see for the input, it's a relatively large answer. I think I'm still doing the input, right? Yeah. It's a relatively large number, but it runs super fast. Why did I use the mouse so little that apparently I'm not on target with it all, but you can see it runs really fast. It's not like a hard thing to do, because this is a fairly large input, right? It's like 140 by 140. Yeah, it's 140 by 140. So, but it's really easy to find all these regions, and then just for each of those things, you just calculate the edges, right? There's not a lot of uh, work involved in doing it. So you get the answer to part one really fast. I don't think a lot of people would probably have a big issue with this because you could kind of infer what's happening and figure it out just by reading the instructions here for part one. Um, it may be difficult for you to like find the perimeter. Maybe it wasn't as easy for you to like do that, and maybe you had to like kind of try and walk the perimeter to find out how big it was. That would have definitely made it harder. But I think the average person could get part one. Would be my guess. If I had to say, obviously, if you're very new, you're definitely upping the ante here for day 12 for part one, but I don't think it's like unsolvable. I think almost anyone with that enjoys or wants to do puzzles could figure this out with a little bit of help. I don't think that was tough at all. Part two makes it tough though. So let's talk about part two because it had me for a whirl. Basically, what it says is the elves are trying to order so much fence that they qualify for a discount. And instead of counting the perimeter as like, each value or each edge of a plot that's on the perimeter, you now want to calculate the number of sides. So this A right here, it had a perimeter of 10, but it only has 4 sides, right? It's got this side, this side, this side, and this side. Maybe even if we go look at this example that I had right here, whereas it had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 before, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it had a perimeter of 10. So part one had a perimeter of 10. Part two, it has 1, 2, 3, 4, 5, 6 sides. So the perimeter or the part two has 6 sides, right? That's the way that's the way it wants you to do. Otherwise, the rest of the problem is the same. You still have the regions, you multiply the number of sides by the area to get to the answer for that region, and then you sum up all those. That part doesn't change. So the only thing that changes between part one and part two is now you're working with sides as opposed to working with with like the perimeter value. This one actually had me for quite a while, to be honest. Admittedly, I didn't work on it the whole day. Like I solved part one in the morning, and then I read part two and thought about it for a little bit, and I'm like, oh, I don't even know how to do that. And so I started, typing some code and mulling around trying to figure it out. Like I think maybe I can just talk about it. A couple things I thought of was like, can you trace these edges on here, right? So assume you have like an enum of like up, left, right, and down, and then along this edge you say, okay, this one is on an edge and it's on the right of this one and the right of this one and the right of this one. Can I say that all of these are x's, or all of these are on the same side? So this counts as one side. They like kind of cancel each other out because they're the same like x value but a different y. That helps a little bit, but it doesn't help in cases where like if the shape, in fact, they give you this example, if a shape is like this, like this is a side right here and then this is a side right here, but doing that logic wouldn't account for like this missing part right here. And so you might consider these to be the same. And so then you have to do some stuff is like, oh, well, does the side then change right here? And if it does, then I need to like stop, and I now know that's one side. And can I just keep walking? The idea is, can I just keep walking the perimeter? And the perimeter would be something along the lines of, you're on a perimeter as long as you have at least one neighbor that's different from you. And I started that coding that out, but it was a lot of cases and I ran out of time. And so I was like thinking about it through the day, like, how do I solve this? Um, like, what are some other ways that you might be able to find the perimeter, or the number of sides, I should say? And I will tell you how I got to the answer because I think it's actually kind of funny. I was doing dishes, I was down. I wasn't doing dishes. I was down, like, straightening up a little bit, and getting myself something to eat. Um, and I say dishes because next to some of the dishes was my daughter's homework, and it reminded me of some homework that I had done with her before, where we were counting the number of sides and corners of shapes. That was her homework. Um, and the idea is along the lines of, let me move this over a little bit. Um, it was like a math page where it was like, here's a circle, and it would ask you how many sides and how many corners. Well, a circle has no sides and no corners. And then it gave you a square, and it was like, oh, it has four sides and four corners. And then they would give you a triangle, and it has three sides and three corners. And then it would give you like, this is gonna look ugly. It would give you, a stop sign, a hexagon, and you'd be like, oh, 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 sides, and it's got 1, 2, 3, 4, 5, 6, 7, 8. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8 corners. I did do it right. I know what the answer is. It's 8, right? What you will notice here, and this is what I pointed out to her when we were doing the homework, I'm like, wow, that's really cool. The number of sides is equal to the number of corners. And so I'm like, you can kind of do a short circuit. You can, if you know the number of sides, you also know the number of corners. And this happened, like, I don't know, it's been a month or so. But when I looked at her homework, it was like I was thinking about this is what came to my mind, and that was like the, oh, hey, that's really cool. This would apply to this problem, right? Think about this shape right here, right? So I'll move it over here so you can see it better. I mean, this is not super accurate to the shape, but how many corners does it have? It has 1, 2, 3, 4, 5, 6 corners. And how many sides does it have? 1, 2, 3, 4, 5, 6. 6 sides. And you can actually do this with any shape, right? So you can get really complex. Here's an E. I'll do one more, just like here's an E, one of the examples you give it. So how many corners does it have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12, right? How does this help you? Well, if it's easier, uh, you could potentially still do something like this, and maybe there's other ways to solve it. But this is the way I got to it: was if you can figure out, maybe you can figure out the number of corners easier than you can the number of sides, and if you can figure out the number of corners easier, then uh, the problem is easier to solve than all of this. And that actually turned out to be the case. So the only question you have to figure out then at this point is, well, how do I figure out the number of corners? And it turns out it's actually not that hard to think about. Imagine, I'm going to draw it like this, like a little hash, and you're interested in this one right here, and you're asking yourself, is it a corner along this way? Right? Does this corner contribute to a corner in the whole grid? The way that you know this is a corner is two ways, right? Either it's convex like this, or is that concave? I don't remember. Or it's a corner this way, or it's a corner this way. I just did it wrong again, right? It's a corner this way, right? The idea being like this is a corner if like it looks like this, or it's a corner if it looks like this, right? Either of those make it a corner. And what do I mean by that is if maybe I should draw it a little bit better and it'll make more sense. If this is the A that I'm considering, it will be a corner if like this is an A and this is an A, but this is not an A, right? Do you see how that forms a corner right here? Now this is a corner like this. Alternatively, it's an A or sorry, it's a corner if none of these are an A, right? So if you have something like this, and it doesn't matter what these are. These could be C's, D's, E's, different numbers. But if these are none, then it looks like this, right? So now you just have to ask yourself, can I do that for all of the items, all of the edges, or sorry, all of the values in the region? There's one more trick to this that I had to figure out is like this is a great way to calculate if this one's a corner, but you also have to calculate like if this side is a corner as well, right? So say this is a B right here, and this is an A right here. This is also a corner right here, right? So I need to figure out, is this a corner right here as well? And you just have to figure out how many of those are corners, right? And it turns out like when you do the math, you'll get like a unique set of corners as you're going through there, right? Because like once you've found this corner right here, like this one will say, oh, there's a corner right here and a corner right here. This one won't find them the same way. And I'll show you what that looks like. But the gist is you can use the logic. I feel like I've made it more confusing. Maybe a better way to say this is once you've like solved it this way, you actually can just do the same thing for all these other corners right here, right? Are these ones corners as well? And if any of those are corners, you just add them all up and that gives you your total corner count. So how does that look in code? Well, to solve it, I basically said iterate over all of the regions, and then for each of the regions, iterate over all of the plots, and tell me the number of times that plot creates a corner in the region, right? So I have this helper function that does that, and I'll show you how it works in a second. Then I just sum all those up and multiply by that region, right? The total number of corners times the region is what's changed here. So as opposed to finding the perimeter, I'm now finding the number of corners, which is equal to the number of sides. And I think I put this in here. Yeah, my daughter Anna. She's the one that the homework got me to go down this path. So what does that corners function do? Here it is right here. I have this corners thing up here to kind of help with this, right? And what is this? Is like it's the four corners of this thing, right? So for this corner side, for this plot right here, for this corner up here, I want to get this value, and this value, and that's what these three are. And then on this side, I want to have this value, and this value. And I call them like this is the opposite. It's opposite to it, and these are the adjacents. And then I just do that for all four sides. So that's what that is. That's what this corners is. So what this allows me to do is get these four values and then just ask this question, these four questions, right? Regardless of what side I'm on, I just need to know which one is the opposite and which two are the adjacent. And I can just ask myself the question, what are the questions I can ask? So here it is. I get the opposite and I get the first and second adjacent values. And then I get the actual value and I can just ask myself the question, are the two adjacent different? And if so, then I'm definitely a corner. Otherwise, are the first and second the same and are the two adjacent the same and the opposite different? And if so, I'm also a corner. So I definitely clean this up a lot. Just to be clear, my code did not look this nice when I first started doing it because I was trying to figure out exactly how this works. But it turns out this is actually enough to tell you if that plot is a corner in that region. And so all you have to do is just ask how many of those parts are a corner of the region, and then you just count all those up, and that gives you the number of corners, which gives you down here, you add all those up, all the corners for all the plots in all the regions, and that will give you the number of sides. The number of corners is equal to the number of sides. So again, shout out to my daughter. She like helped me get there. But this was not an easy problem, at least in my mind. Maybe I say that laughing a little bit because the solution to it was my 6-year-old daughter could have told me how many sides there are to any shape. Well, it's the number of corners, right? And to me, the number of corners seems a lot easier to find than any other solution. So I definitely don't know if this is the fastest or the best. I waited to like look through too many of the Reddit stuff before this video so that I could kind of go through it live with you guys. But hopefully you get the gist of my two parts. Part 1 was not too tough. It's just a question of like, can you figure out how to determine what the perimeter is? And this math was not too hard. Part 2 definitely threw me for a whirl. And it was a day that for part 2, if I had been doing this 5 or 6 years ago, I probably would not have completed it. And you can actually see that in my record for Advent of Code. There's been several years where I got to like day, I don't know, 12, 13, somewhere in this range. And I could only do the part 1s and never the part 2s. And the only way I ever got the part 2s was to actually like get some help and look up a solution. So you might be in that boat too. These days start to get harder like that. And I've had days before, even last year, where I just didn't know the solution. And so I had to get some help. So, and this one, I technically did get help. I got help from my daughter. She helped me figure this one out. So there you go. Because I was really struggling with this part of it right here when I was like thinking, oh, is there some way I could kind of trace the edge and figure out how many sides there are? If you did that, I would like to see your solution. I don't have mine anymore because I wasn't handling these weird edge cases like this. Like my initial thinking was like, oh, I can just kind of go along here and along here and along here and along here, here and here. And that will give me, I now know there's 1, 2, 3, 4, 5, 6. But it turns out that is that 1, 2, 3, 4, 5, 6, 7, 8. Yes, it's not the case, right? Anyway, I was trying to figure out ways, but there were just so many edge cases that it got complicated enough that I'm like, how do I do this? And so again, thanks to my daughter, I was able to solve it. So it's just another one of those. Don't feel bad if you're struggling to get there, and don't feel like you can't reach out for help or in figuring out the problem or understanding it. And so we're going to go look now. That's what I want to do, is I just want to go look and see how other people solved it. Obviously, I'd love to see how you guys solved it. Let me know how you did it. Maybe you found another cooler way, and we'll try and get there. So day 12 AOC me. Let's go in and out. 20-minute adventure. 2 hours later. Yeah. I was totally in the same boat. Day 1, our part 1 of day 12 was like, I think it took me like, I don't know, 10 or 15 minutes to code this and get it running. Not tough. I think I had a bug in here somewhere. I'm trying to remember where it was. I don't remember where it was, but I had a bug in here that gave me the wrong answer. I was able to fix it relatively quick, but it was like it took me like 10, 15 minutes to solve this. Part 2, again, I worked on it for like a half hour, 45 minutes, and then I had to give up because I had to do real stuff. And it wasn't until I spent a lot of time thinking about it throughout the day daydreaming or whatever to get there. So I could definitely see how this would take forever. You finish it. People able to complete day two. Oh no. Don't give up, dude. Keep trying. It's okay. It's okay to not be able to solve it. Can I just say that? If you are learning, you are uh, your stars count just as much as the next person. Maybe I should just say don't give up. Don't give up. Yeah, don't have this attitude, seriously. I know a lot of people say like, "Oh, it's too tough for me. I can't go any further." But if you've learned, there's been days before where it's all like you have to know some archaic math problem to solve it or whatever, and I just didn't know the math to it, and so I had to go look it up, and that helped me. But at the time, I'm like, "Oh, now I understand the math." A couple years back, I didn't know what the shoestring algorithm was, or I think that's what it's called, and so I had to look it up. Uh, Yeah, definitely don't give up, dude. You got this. You got it. It's okay not to know. Yeah, I was in tears. I was in tears. Is there a reason these plots could be made rectangular? Sorry. Yeah. Good old Field of Dreams. Oh, this is day 11. Oh, this is a cool illustration of the previous day of like how quickly you can like, oh, I've already seen this before. I can skip, right? You skip so much of the tree. Oh, this is cool. Kind of doing a flood fill, visualizing all the stuff. How is it picking which ones to start with? Does it just pick one at random? Minecraft. Okay, that's cool. It totally is a Minecraft thing, right? That would actually be kind of funny is to go look at your input and build a Minecraft plot like this. That might be fun. Kind of hilarious. It's been 84 years. We have had a lot of neighbor algorithms recently, right? Well, part of the things is I think I've joked about this before is you can treat everything as a graph and neighbors and stuff like that. The nice thing you can't treat everything, but you can. Most things are like, oh, I can make this a graph, and then the nice thing about doing that is you know how to solve it now, right? It's because you can say, oh, I can use Dijkstra's or I can use whatever a star, I can use a flood fill. All of those things are perfect. Day 12. Oh, that's kind of cool. He's clicking around, finding the things. I'm not into gardening anymore. I did use a lot of hash maps in my code. The tricky grid indices, edge cases, 4x code duplication. Okay. Why does the master theorem have such a pretentious name anyway? What is the master theorem? I thought I was so clever. Assign each perimeter grid to its own partition. Divide the partition down to unit size. On the way back, merge the partitions from left and right trees. Much like union find, realize a space in between two nodes in the left partition might be filled by something in the right. I actually don't understand what that means. Yeah. All shapes have four sides unless you can't like a nerd. Okay. You can fit any shape into a triangle, really. There you go. So what is he doing? He's counting all of the parts of the region where there is a yeah, see, this is kind of what I was trying to do is like, can I like draw out the perimeter this way? You basically like go through it and say, hey, how for each of the plots in the region, how many of them, contribute to a perimeter, and then how many of those are like adjacent to each other? I don't know if this helps you solve part two though, because is it 32? 1, 2, 3, 4. I don't know if it is. Here's a nice visualization. Today was a hard on. Okay. Did anyone do it differently? Maybe we should just. I'll spend a couple minutes looking and see if anyone. It feels like a lot of people had the same issues as me. Part two, much harder. Counted the number of edges rather than the number of vertices. Map the edges of each plot, then count the edges that appear 1 or 3 times, and do some special case processing for implied edges appeared twice, as hinted in the puzzle description. Where does it talk about that? Oh, it's this section here. I think he's talking about Mobius fencing. Yeah, I forgot about that joke. Very good, very good. I don't usually like reading Java code, especially when it's in Topaz. Nodes, edges, neighbors, region. Yeah, I don't want to read this. Someone posted a solution using convolutions for the hiking path puzzle on day 10, which I liked, and I thought this was possible too. And the image label, and you can find objects from SciPy. Crops, kernel, funny kernel. Find edges of a convol 2D. I actually don't know. I actually don't know how that's working. So this is another math one that I'd have to think about. If I didn't do it live, I could do some research. So it's doing a 2D convolution. Oh, this is getting the total number of edges. Okay. No, it's not. It's getting the number of sides. I think this one's getting the number of sides doing a convolution. I've never seen it work that way. Interesting. Okay. For both parts, I used a DFS to construct the regions, which I represented as a set of points. What did I use? I think I used a set, didn't I? I used a map in my garden, I'm pretty sure. Yeah. Oh, but I think I do use a set for the regions, right? Yeah. because it's really just a list. The region is just a list, right? And so it doesn't really matter what. There's no like quote unquote value. They all have the same value, I guess is what it is. To find the perimeter in part one, just checked every point in the set and counted up how many of its neighbors were not in the set. Yep. I mean, I did it the same way. I guess I did mine backwards, but like it's the same thing. For part two, I was a little stumped until I saw the number of sides would be the same as the number of corners. Okay, so he solved it the same way. Ooh, where was the hint? I'd like to if someone figured that out. But he did it the same way as me, right? Basically, it said. I mean, take me a second to grok this filter ID top left. Okay, so you get all the different corners, and then you do some. Oh no, it's gonna return these. You filter. So the top left is where. Oh, these are the convex and concave ones. So top left, top right, bottom left. These are all the convex ones, meaning like I think I talked about this before, right? Like uh for this one, I don't know, for this one right here, this corner going around here makes this one concave and this one convex. I'm sure I mixed those up, but that's just what he's doing right here. So he's basically doing the same thing. He's like, hey, is this in the set or are these both in the set and then this one's not, right? Yeah, right here, right? Are all of these in the set and this one's not? So these are the concave ones, right? Okay. Flood fill for part one. For part two, count sides by counting corners. Okay, good. Counting corners. Apparently, I'm not the only one. I wonder how many of them had their daughter help them find the solution too. Programming breakdown. I mean, I don't understand basic, but I don't mind reading a summary. A stupid but working 5-liner. I need to go to bed. Yowzers. It is very fun to look at these, but also like if I saw this in a pull request, like downvoted. Um, but for these problems, these are really cool to try and figure out how to do it. I think I saw somewhere programming language that uses salesman speak. Man, I don't know if I can find it again. But it was using things like buy now and you won't believe the deals for like if statements and while loops and stuff like that. It was really hilarious. Anyway, it was really hard to grok, but like just like this one. Anyway. You can solve part two without counting corners if you represent a border as the two cells with different plants. A union find on consecutive borders. Oh, that would be much easier. That might be easier. Like for the way that what he's saying is like at least if I understand it right. Assume you have like O A O. Like if you know like say you're here at the A and you know like this is an edge right here, you just do a DFS to find all the other edges that are on this same side. So like you go here and then here, and now you can mark these three as visited, and you say this is one side, so you don't have to visit this one anymore. But then you can go this way, and then you do this one, go here, and here, and then you DFS here, and then you mark those off, and now that's another side. So you do the DFS. It's That's a cool. Okay, that would definitely do it. Okay, I like that. Yeah, I was really trying to figure out how to do that. It is recursive as well, too. That's really cool. We got a thumbs up this one. Very cool. I did not know this. So the idea, yeah, again, the idea is when you find an edge, you DFS to like remove the rest of it from the edge. So like you keep going down along the same ones until you don't find it. It doesn't feel as, I mean, the code is pretty clean. There's still the edge cases you have to figure out though, right? Is like if the like say you found like these three are on the line, like if this is part of it too, you now have to say, oh, this one stops because this is not part of it, right? So you do have to do some work to figure that out, but you basically like do it. You start at a perimeter and you like do a DFS through the perimeter to find out where it goes on the grid. But that is cool. The idea is the way, maybe like a higher level way to think about it is like once you've found one that's part of it, you like you say to yourself, well, which ways can I go? And so if I can go this way, I walk all of that way and mark all of these as like used until I come to something that changes it. And then I try it this way too, and how does that move? And maybe it only goes up a couple, but that would totally work too. If you solved it this way, that's really cool. I'd like to see your code, especially if it's like in Rust or something. Yeah, you can see. So here's where it's happening. You do this like visit side, and then you like visit the sides recursively to make sure they're still the same, going the same. Side is visitor side, not in borders. Return. Yeah. You just got to make sure you keep going the same way. That's very cool. Very cool. Very cool. Okay, I like that solution. That feels a lot easier than what I was trying to do too. With my first solution, I actually think the corners is probably the easiest one, but it is a trick. This is one you could kind of get to with programming. Continuing down like the dynamic programming path is maybe the way to think about it. Let's look at a couple of Rust ones and then we'll be done. Went from one with one of the ugliest solutions to one of the cleanest after I decided I cannot have this mess. Okay, let's see what it looks like. Calculate fence and corners. Part 2, okay. Okay, I think he's doing some logic here on U8s. He may be going for performance, and that's why he's like not. I don't know if you have to cast any values in this one. Sometimes casting takes time, and so you may do these operations. Panics if out of range. Returns true if the plan has been marked visited. Okay, so he's like visiting within the graph. Oh, he sets it to Z. Sets it to outside Z if it's outside. Or it's been visited. Okay, that's what he's doing. So his mark sets it to above Z to like say I've seen this one. That's an interesting approach. Like what does it net you? I guess you're like mutating the same grid. And so maybe that gets you faster performance wise. I actually don't know. I didn't even try to see how long it takes my stuff to run. Check it really quick. I mean, they hardly take any time, right? 3 milliseconds and 4 milliseconds. I mean, it's hard to compare straight across, but what does he say his takes? 170 and 262. So that's like an order of magnitude faster. And I'm sure it's just because my guess is like I don't know that my solutions is any slower than his, other than I'm just doing like copies and stuff like that where he's probably not. Maybe that's why it's saving him time. It doesn't feel super readable, but I mean it is super fast. Calculate fences and corners. So is he doing the corner one? He's solving it the same way. He's just using a different way to track. What is this wrap ad? Oh, doing the wrapping. Okay. This is just one of those things where like they're U sizes. Is that right? It's like a U size, and he doesn't want to cause problems. I mean, I have found some tricks that are helpful with that. You actually see, I think I do it here too. You iter over the U sizes, and then you cast them to I sizes here, so that you can do the simple neighbor arithmetic, like right here, for example. This stuff probably slows it down too, that I'm not doing it hard coded. It looks like some of his stuff is hard coded. I have Chrome up, by the way, because for some reason I can't get this whiteboard to work well in Firefox. So that's why I'm using Chrome for that. That's why I'm sorry you're seeing a little confusion. Instead of using a recursive algorithm, he keeps it on a queue and just works with it. Okay, yeah, that's fine. He pre-Alex. So he is. These are things that lead me to believe that he's going for like performance, which is cool. I think I've talked about this before in years. Some people have the goal of like, how fast can I get all of my days and even all of my years? Like, what is the sum total of all of my years? And some people have it still in under like the sum total of all of the years is like under a couple seconds. It's absurd how crazy fast they can get these things. I think the ones that I've seen are in like Rust and C++. And it's absurd how fast they get. But okay, it looks like though he solved it the same way I did. He just is going for speed. That's very cool though. Very awesome stuff. I need to try lining these. I need a hint for part 2. OTL. What does OTL stand for? Am I going to regret searching for OTL? Opportunity to learn. Yeah. That's the thing, like I was saying right at the beginning, right? It's okay if you don't know the answer. Again, I did not know the answer. My daughter helped me. follows the walls, but didn't have an idea for how to handle the islands. Yeah, I had to say, ooh, the islands. I hadn't even thought of the islands. That's crazy. Because like you can trace an outline, but then you don't like right if like let's say you're like right here, what I was talking about before, and you kind of like trace this outline of it. If there's like some hole right here, that causes a problem, right? So I didn't even consider that would have made my initial solution like even worse. Worse solution somehow to keep track of walls as objects and could look for a hint and saw someone mention counting corners. I'm a little sad I didn't come to that realization on my own. I also did not come to the realization. I mean, I technically did, but I was reminded of my daughter. I'm a little sad I did not come to the realization on my own. Yeah, no need to be sad, dude. This is the thing is like, I mean, oh, I didn't solve it on my own. That's okay. We're all learning. There's days that I have absolutely no idea. When I first started, like every day was like, what am I doing here? You just got to push through the I'm a worthless programmer because it turns out we're all worthless programmers. Um, there's always someone better, right? Looks like he's doing a flood fill for the region finder. Yeah. I see a lot of people doing this, and this is totally okay, right? I don't know. Yeah, what do you guys think is what do y'all think? Like is doing something like this and then something like this so that you can make a call like this? Is that more readable or less readable than doing something like this, where you just like literally have the values and you do the arithmetic to get the new positions, right? Like I presume that's what he's doing. Gets the new positions and then adds it to his list, increments the perimeter if something's out of the region. This is doing more than the flood fill, huh? It's actually finding all of the values, but how many are um how many are on the perimeter. So this is this flood region must be for the whole of part 1. Yeah, like here's where he adds it to the area, here's where he finds the edges, and then he marks it here as visited. Mutable slice vec bool. Interesting. Okay, so like if he pre-creates, that probably helps a lot. Is that what he's doing? Where's his main? Yeah, he does. He pre-computes small defaults. Okay. I mean, it definitely is memory, but it probably is faster. Can be faster than like asking every single time in a hash set. I actually don't know. That's a good question. I mean, this is it. It's got to be faster, right? Asking asking is this visited here is probably is surely faster. They always say like, oh, it's 01. Well, I mean, this is 01, and like a hash set query is 01 as well. Like, is this in the hash set is 01? But you're doing counting, right? I mean, you have to do your hash and do all that stuff, so it's technically not as fast. Okay, one more Rusty. Had my first serious fight with the borrow checker on this one. I mostly won and learned a lot. BFS to find the regions. Yep. BFS, DFS, flood fill. They're all kind of the same thing. Count over the neighbor cells for part 1. Count outside and inside corners separately for part 2. For outer corners, I go through board. Is he using a board corners too? Everyone has a daughter apparently in kindergarten, or potentially just remembers what they were taught in kindergarten, which I did not. the sides. Some of these things I do not know what they are. Tuple combination. Are you doing like a combinatorics on the tuple of the values? Filter. I'll have to read this one more to understand. Tuple combination. I won't read it right now. Get regions. What does he say about it? What are the outside ders? Am I just missing half of his code? Oh, here, there. Ortho dir. The orthogonal directions in inner filter dr contains d plus d. So this is what is r here? Okay, so it is. I presuming this hash set point is like the region. I think it's saying so. This outside ders is saying find any like edges. You're essentially finding an edge here. Edge tuple combination. I don't know what that is. I just presume if there's like three, you're doing like a combinatorics of the three, and you're filtering where it has a corner. I wonder if I could use this tuple combinations. I'll have to try it. Where's it even coming from? Is this just a Rust thing? Oh, it's in iter tools. Return an iterator adapter that iterates over the combination of the elements from an iterator. Yeah, it is the actual doing combinatorics. Okay. Interesting. I did not know about that. That's kind of cool. So you basically get all the outside edges, you find all the combinations of them, and filter only by the ones that has corners. I mean, this is a really interesting way to do it. Like, if I understand it right, what it's doing is like, given A, it's finding all of the other A's in these things, and it's filtering by this has corner. So it's doing like a combinatorics of this one to this one, 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 you know, this one is so on and so forth. But only when it's when it's not part of it, and somehow that gives you the outer and the inner. This is lost on me. If you understand how this works, I would love to hear it. The borrow checker is hard. It's okay though. I hear about this a lot in Rust when I'm programming in Rust. Even when I've talked to people before, they're all like, "I can't do it. It's constantly failing." And like the reason it's failing is because it's saying you are not being memory safe and you don't understand what your code's doing. Um, and I don't know if you've seen, but on many of my days, it does not look like I understand what I'm doing. Right when I was doing the live solves, and so I do have to spend a lot of time with the borrow checker. Right, so I need to dereference here so I can get a an actual thing. Alternatively, you could. That one was a funny one to pick because I can just pass these by reference. In fact, I probably should do that. Should I do it right now? Because I'm not changing any of these. So passing by reference should be okay. Consider borrowing here. Oh, that's gonna screw these up because of the ad. It's like I need to change each of these to wait, I think I remember something from last time. How do I want to do this one? I did that wrong. One more time for the money. We go. Like that. Oh, this one was silly because I can just do this now. Like that's what it wants me to do there. And then I don't have to do it right here. And dereference the oh, you know what? I can do this. Then do I just implement copy for oh, I have implemented copy. I can just dereference it. But it does mean I have to fix this. Then I dereference here to get a copy. And neighbor is a what? Pointer. There you go. So now I'm not doing all the copies. When it says like fighting this is the thing is like, right, is it will fight you a lot and say, oh, you're not doing that right. Sometimes the code doesn't look as good. Sometimes it could look better. But it is important to think about this stuff. And that's why I think it's helpful is you're like, oh, I'm not changing this. I can use a reference instead of a copy. It will not speed up my code significantly, I don't think. I mean, that's it's hard to do it with just one sample, right? It's still in the same order. Anyway, you can see like thinking about this in Rust is important. So, okay, I've looked through a whole bunch of solutions. We've gone well over an hour. I was having fun just looking around. So, anyway, hopefully you enjoyed the day too. If you struggled, don't feel bad about struggling. Again, this one took me most of the day. Admittedly, I only was programming for like, I don't know, an hour and a half total. A lot of it was trying to mull through my mind how I do it. So don't feel bad if it takes you a lot of time. And don't feel bad about getting hints, right? Days will require hints. And so if you need a hint, that's okay. In fact, we're getting to the end where I think I'm going to try and do a live solve again over the weekend. And I'm sure there'll be days over the weekend where it's just like, I don't know the answer. We got to go look something up. So it's okay to be that way. You're learning and trying to figure out, right? So hopefully you enjoyed the day and the videos. I definitely am enjoying it and love to keep doing Advent to Code. You can see I'm slowly getting up to all solves. Where am I? Day 2022. I think this one's the int code that we're not quite done with. And then I have 1, 2, like maybe a total of 2 years, like a half a year here, half a year here, 1 year here to get all the way caught up. Some of these I don't know the answer to and just had to work through. But I really enjoy Advent to Code. I hope you like it too. Keep doing your best, getting out there, trying it. And if you struggle, feel free to look it up. Hopefully this video helped you, right? So we'll talk to you later.